Of the countless aged stars throughout the universe, some die quietly, leaving hardly a trace. But others refuse to go gently into that endless night, and they end their lives in a stunningly violent explosion.
Our ancient ancestors were aware of the sky and the changes that occur in it, and they attached special significance to some of those changes. But usually they were regular and predictable variations, things that occurred in the normal cycles of the sun, the moon, the planets, and the stars. Every once in a while, however, something unforeseen would command the attention of an entire people. An eclipse, a comet, or perhaps a guest star, as the Chinese quaintly called a new star seen where none had been seen before. These objects, these new stars, were also called novae, which just means new. And sometimes they were bright enough to be seen in the daytime, and they could even cast shadows at night. And one such spectacular event occurred in 1054 AD and was witnessed by Chinese and Japanese astronomers. And until recently, it was thought that they were the only ones who observed the event, except possibly Indians in the American Southwest. But a new account of an observer in the Middle East at Constantinople has also been discovered recently. Of course, in 1054 AD, no one really knew what a nova or a new star was. But today we realize that there are two completely different reasons that can cause a star to suddenly appear where no star had been seen before. And we're really not dealing with new stars, but actually old stars. Now, what's called a nova is a peculiar situation in a binary star system where a cooler star, expanding, dumps some of its material onto a smaller, hotter companion. That star brightens up hundreds of thousands of times more than it was before. But it settles back down again, and the system afterward is relatively little worse for wear. It's also possible, however, for single stars to brighten explosively, and this is what happens in a supernova. Stars that are more massive than the sun, sometimes considerably more massive, destroy themselves as they explode to briefly become hundreds of millions of times brighter than normal. And it was a supernova that was observed in 1054 AD. Well, accurate Chinese maps allow us to look now, 900 years later, back in the same place where Chinese astronomers saw that event. And there today we can see the remnant, a cloud explosively expanding outward into space.
Basically, the whole history of a star's evolution can be thought of in terms of the struggle of the star against the pull of gravity. Right from the time when the star forms till its death, the star is trying to push back on the gravity, which is trying to pull it down to a point. Most of the star always counterbalances gravity with some form of pressure. And the question then is, where does that pressure support come from? If the pressure support is ever taken away, the star will totally collapse, and this is what happens in a supernova explosion. Well, for the most part, stars get their support against gravity, that is their pressure, from the heat of the gas in the interior. That heat is usually provided by nuclear burning, that is transformations of hydrogen nuclei into helium nuclei. This is what takes place on the main sequence. That is, during main sequence evolution, the stars are burning hydrogen to produce helium. This is keeping their interiors hot, and so they are fighting against gravity. Now, in lower mass stars, once the hydrogen has been used up in the centers, it's possible in certain circumstances, and depending on the particular mass involved, for the star to use another form of pressure, one which isn't so commonly known about. And this is a pressure which is due to the degeneracy of the electrons themselves. It's called electron degeneracy pressure. It doesn't depend on the temperature of the gas at all. But massive stars, that is ones above about 10 solar masses, or perhaps a little bit lower mass, don't encounter electron degeneracy pressure until very, very late in their evolution, if at all. And so their evolution is not bedeviled by considerations of electron degeneracy. The main effect of electron degeneracy pressure on low-mass star evolution is to terminate the evolution before many burning phases have been accomplished. Higher-mass stars can go through a large range of burning stages.
The explosion of a supernova is one of the most spectacular and rare events in the entire universe. In these cataclysmic events, a star increases in brightness millions of times within a day or two, and then slowly fades away. At peak brightness, a supernova can outshine the whole galaxy of stars to which it belongs. There are several reasons why a star might self-destruct, and the determining factor is its mass.
A star will go supernova, that is, explode or implode, when the pressure support is totally removed. The star is trying to support itself against gravity, and to do this, the only thing it has is pressure support. And if for any reason that pressure support is removed, then an implosion will take place. Depending on the particular mass of the star and the run of the star's density with radius, we might have either a total implosion of the star, or a total explosion, or part implosion and part explosion. If you have an implosion, you're going to get a condensed remnant formed. And if you have some material finally exploding out of the star, then you will get a diffuse remnant formed. The particular causes of the supernova, that is, what removes the pressure support in a particular star, depends on the mass range of the star. Only stars more massive than with an initial mass, that is, larger than about 4 or so solar masses, are going to go supernova. It's now thought. Stars in the mass range of between about 4 and 8 or 9 solar masses will probably go supernova when carbon detonates in their cores. That is, they go through hydrogen and helium burning, but then when carbon ignites, instead of doing so very quietly, there will be an explosion. And the reason for this can be understood thinking a little bit about what the core is like. The core at this time is supported by electron degeneracy pressure. That is totally insensitive to the amount of heat around. And so what happens when the carbon ignites? The heat content in the core goes up and up and up, and the core doesn't adjust at all. And eventually you get a thermal runaway, and vast amounts of heat are liberated. And before the star knows what's happened, an explosion has taken place.
More massive stars than about 8 solar masses ignite their carbon non-degenerately, and they evolve rapidly through several stages of evolution, several stages of burning. You'll burn your carbon into an oxygen-neon mixture. The neon will photodisintegrate into an oxygen-magnesium mixture, and the oxygen then burns to a silicon-magnesium mixture, and the silicon burns to iron. So you develop an onion skin model of a star where you have a hydrogen envelope, a helium shell, carbon-oxygen shell, and all these shells down to an iron core.
And once you form an iron core, then nuclear reactions shut off unless you add energy. Getting energy out of iron is like getting money out of the government. It can't be done. Iron is the most tightly bound of all nuclei, so that when the iron starts forming, it undergoes no further nuclear reactions. The core just builds up until it becomes energetically favorable for a new kind of reaction to take place. It's not a nuclear reaction, it's a particle reaction in which protons and electrons combine to form neutrons. And because a neutron is much smaller than a proton plus an electron, the result is a sudden and catastrophic collapse of the core of the star. It goes from a diameter like that of the Earth, thousands of miles, down to a diameter of 10 miles in a microsecond, and releases in the process vast amounts of energy. That energy manifests itself in various ways. It makes the star get bright so we see it. That's how we know about supernovae. It also does other things. It blows material off the star, which is interesting from our point of view because the material it blows off contains the carbon and oxygen and magnesium and silicon and so forth that the star has been cooking over its entire lifetime. And the heavy elements in the Earth and in our own bodies were cooked in previous generations of supernovae. In addition, some energy goes into neutrinos and gravitons that we don't quite know how to look for. Some energy goes into cosmic rays, high-energy particles that continuously bombard the Earth and everything else in the galaxy. And finally, some energy goes into kinds of nuclear reactions that can only occur when you have lots of energy, in which neutrons are added to things like iron and build up all the heavy elements, silver and gold and platinum, less interesting things like barium and gallium.
Then if you go to very massive stars, perhaps larger than about, well, more massive than about 80 solar masses, perhaps even 100 solar masses, you get to a situation which is again different. At some stage during the evolution, the temperature gets so high in the interior, above about 10 to the 9 degrees Kelvin, that many electron-positron pairs are formed. These electron-positron pairs then annihilate one another to form high-energy photons, that is, gamma rays. Again, when this happens, when a large number of electron-positron pairs form and produce gamma rays, again, the pressure support in the star is removed. And this can happen at any stage during the evolution. It just depends on the details of the interior, when the temperature gets high enough. And again, you have a supernova explosion.
In a supernova explosion, it's believed that as the nuclear fuel is burned, the outer layers of the star start collapsing toward the center. If the star is very massive, there is no known force that can prevent it from being crushed to about 10 kilometers in size, retaining the same mass. This is similar to crushing the Earth into the size of a football field. As it gets smaller, it spins faster. And since the amount of matter is essentially the same as when it was a larger star, its magnetic and gravitational fields also increase in strength. In a neutron star, the collapse stops when the atoms have been crushed together to an extent that instead of having separate protons and electrons, everything is combined into what's called a neutron soup. Now, if a neutron star is in orbit around a normal star, like the pair of stars in Hercules, then, as the normal companion loses mass, the gravity from the compressed star captures the matter from its neighbor. As the matter falls into the magnetic poles of the neutron star, it heats up to very high temperatures and shoots out a stream of energy, X-rays and gamma rays, which satellite observatories will be able to record. When the magnetic poles are not the axis of rotation, every time the star rotates, the stream of high-energy radiation is swept through space and appears to us as a pulse. Most pulsars emit primarily radio light, however, and do not necessarily have companion stars.
The Crab pulsar was discovered first by radio astronomers at the National Radio Astronomy Observatory at Green Bank, West Virginia. And all they could tell at first glance was that it was located in a certain area in the sky, notably an area including the Crab Nebula. The Crab Nebula is a very peculiar object, and so the inference was that the pulsar was actually located in the Crab Nebula. Now, this nebula, which was the result of the supernova explosion that was observed in the year 1054, is a very peculiar thing in that before the pulsar was discovered, there was a great question as to how the energy that drives the light coming out of the nebula was created. Now, there just doesn't seem to be enough energy resident in the nebula at any one time to provide any kind of a bank or storehouse of energy that would lead out. And so the problem was, well, we need a continuous input of energy into the nebula. And there seemed to be no known way of doing this until the pulsar was discovered.
Well, one astronomer has said there are two things to study in the universe: the Crab Nebula and everything else. Well, of course, this is an exaggeration, but the Crab Nebula has taught us a great deal about stars and is the site of many famous firsts. For instance, the first pulsar to be seen blinking in visible light was found in the Crab Nebula. Well, pulsars are actually objects that were first detected in radio light. And in 1967, Jocelyn Bell Burnell, who was then a graduate student, noticed strange, rapid, and regular pulses of radio energy coming from space. The blinking was occurring just once over every second or so, like a radio beacon in space. And it was quite unusual. Nothing so regular or rapid had ever been seen before. And this led some individuals to speculate that it might be a message from some extraterrestrial beings. But soon more of these pulsars were found. And eventually it was realized that pulsars were just neutron stars, highly compressed cores of stars that had exploded in supernovae explosions.
These supernovae explosions may be the result of a very massive star collapsing in on itself and falling right through the white dwarf stage. Then it might explode in one of the greatest displays of fireworks in the universe. The collapsing star, or the part left behind by the explosion, might continue to collapse until the elementary particles, such as neutrons inside the atom, could be compressed no further.
Now, the cinder that remains after such an explosion, the neutron star, may be only a few tens of miles across, but it's exceedingly dense. In fact, one spoonful of it can weigh 1 billion tons. And the object is spinning around rapidly, and it's rotating so fast, in fact, that the fastest of all is going around 30 times a second, and it's located in the heart of the Crab Nebula.
The cosmic debris from the supernova explosion that created the Crab Nebula still remains. It was nearly 1,000 years ago when we saw that star begin to die. In a titanic death rattle, it expelled tenuous glowing filaments of hot gas, which now emit large amounts of radio energy. Recently, radio astronomers discovered the remarkable pulsating signal coming from the remains of the shattered star itself. It was the first pulsar to be so precisely identified. Radio bursts from the pulsar recur with astonishing regularity. Like a lighthouse beacon, the pulsar flashes light and radio waves into space. The dying star has shrunk, collapsing under its own weight, and is now no larger than Manhattan Island. The crushed sphere contains the mass of the sun in a ball only kilometers across. 1 teaspoonful of its matter would weigh 1 billion tons. The rhythmic emissions from the pulsar are the final heartbeats from the star. In a few thousand years, it will slow its rotation and fade from the heavens.
To explain the radio pulses has turned out to be quite easy in one sense and yet difficult in another. The pulsar is supposed to be, well, radio pulsars are supposed to be rapidly spinning neutron stars with strong magnetic fields in them. And when you have such a spinning magnetized body, it acts like a generator. Any electric dynamo operates in essentially that way, a spinning magnet. So you get electric fields. And electric fields can accelerate electrons, and accelerated electrons, very fast electrons, love to radiate. Indeed, they like very much to radiate in the radio, at radio wavelengths.
The measurement of these radio wavelengths requires a lot of energy to be gathered in a very short time. Radiation from the star is focused by the enormous reflector or dish to a point, in fact a line 500 feet in the air, where the information is fed to a receiver and then to the chart recorder or computers. One pulsar was found to have its period of pulsation getting slowly longer by 36 billionths of a second a day. This minute difference was a crucial and critical discovery. It showed that not only were the pulsars natural sources, but they were in fact spinning tops, gradually slowing down. As the massive star collapses, the rate of spin is greatly increased and intense magnetic fields are built up. The result is a rotating beacon which sweeps the cosmos, from which flashes of energy can be observed. Eventually, the spinning slows down as the energy is used up. As observations of aging stars continue, there may be the possibility of associating other phenomena besides pulsars with supernovae.
It's thought by some people that supernova may trigger star formation. What may happen is if a supernova goes off quite close to a cloud, then the shock wave coming out from the supernova could impact on the cloud and help to condense certain parts of it and start off the star formation process. The indications are that this may have happened in the formation of our own solar system. It's been suggested by two astronomers, Cameron and Truran, that there was a supernova trigger for our solar system. And this is based on observational evidence that there was, at the time of formation of our solar system, quite a lot of the nucleus aluminum-26 around. Now, aluminum-26 is a very short-lived nucleus. It's radioactive. It only lives a few times 10 to the 5 years. And to have that around in this early solar system implies that the star in which it formed actually supernovaed only a few times 10 to the 5 years prior to the formation of the solar system.
One interesting observation that the X-ray astronomer has found only during the past 5 years or so is that the remains of exploded stars, which we call supernova remnants, are intense sources of X-radiation. And this is a very important finding because these remnants are difficult to observe in visible light. They're just very, very faint, diffuse wisps on the sky, even when exposed at the very largest optical telescopes. But it turns out in X-ray light, they are relatively bright and are therefore quite amenable to study. We now know of more than a dozen such objects, which we think are sources of X-radiation simply because they're so hot. We're seeing the glowing hot gas that are the remains of these expanding supernova remnants as they plow into the surrounding rather cold interstellar gas.
Throughout our galaxy and beyond, there are massive stars approaching the last phases of their lives. But exactly when any one of them might go supernova isn't known.
Toward the end of a star's life, the nuclear processes inside go on so fast that the outer layers of the star don't know what's happening, so that a star 10 minutes before the supernova takes off doesn't really look very different from any other red giant. There are, however, a couple of nearby massive red giants whose total lifetime from the exhaustion of the hydrogen fuel to supernova is only something like 10,000 years, so that we know that they'll have to go off sometime in the next 10,000 years, though we don't know when. The two closest stars of this type are Antares and Betelgeuse, and there's roughly a 1% chance that one of them will go off, say, in the next 100 years or in the lifetime of the hardier of our viewers. It's been calculated that the optical brightness of such a supernova would be comparable with that of the full moon, and since the light would be from a point instead of a surface area, I think it would look even brighter. In addition, after a few hundred years, the cosmic rays from the supernova would strike the Earth's upper atmosphere and undoubtedly cause various chemical changes there, possibly destroying the ozone layer, if we don't do it ourselves first with aerosols, and possibly also greatly increasing the mutation rate on Earth. People have sometimes claimed that terrestrial evolution goes through rapid phases just when there happens to be a nearby supernova.
Although still speculation, it has been suggested that sources of cosmic rays, which are actually high-speed subatomic particles rather than true radiation, may be found in exploded stars like the Crab Nebula. This luminous cloud is the remains of a star that exploded more than 50 centuries ago, but it may still be emitting a continuous stream of cosmic rays. It's known that high-energy cosmic rays travel through space at speeds approaching the speed of light. These are called primaries. When a primary strikes an atom of gas in the Earth's atmosphere, the cosmic ray shatters it into many particles, among them neutrons, protons, and mesons. These are secondary cosmic rays. The secondaries have enough energy to shatter still other atoms in the atmosphere, and so a growing shower of particles cascades down toward Earth. It is the secondaries that are detected on the ground. This shower effect can be recreated in the cloud chamber with sheets of lead to represent atoms in the atmosphere. From experiments like these, scientists have learned a great deal about the nature and energy of cosmic rays, and have obtained a more accurate picture of their interaction with other subatomic particles. Scientists have proof that cosmic rays, like any other electrically charged particle, are affected by the Earth's magnetic field. When primary particles approach the equator, many of them move perpendicular to the lines of force and are deflected. Only those with the highest energies penetrate to the atmosphere. But at the poles, many particles approach parallel to the lines of force, and even the weakest can reach the Earth. Perhaps the study of cosmic rays may someday tell us more about the explosions of some dying stars.
Our own sun will not experience a supernova explosion. But although this fate doesn't await us, supernovae are still important to us. It's believed that supernovae are the events which, through the depths of stars, seed the cosmos with the heavy elements forged in the thermonuclear furnaces. These heavy elements weren't around at the beginning of the universe, and so neither were planets like the Earth or creatures like ourselves. There's another interesting lesson also to be learned from supernovae, however. They're a good example of how science and astronomy work. Neutron stars had been predicted long before they'd ever been observed, and supernovae were known about. But with the discovery of pulsars, these two ideas and objects were brought together with the third to put together a sensible picture of how it is that certain stars eventually wind up, what their ultimate fate is. Well, things don't always work out this well. Explanations don't always come this easy in science or astronomy. But in this case, we can understand the stars better and even take some satisfaction in knowing that out of the furious deaths of stars, new stars will be born.